So I have just started recording in principle so that if anybody is interested in any of the slides, I am going to post them later today. Are there any undergraduates here? All right, so if you want, yeah. So anybody who's an undergraduate, you have just been accepted to an online math summer research program if you want it, and I'm happy to talk to you about details about that afterwards. So just for coming today, if you want to do math research over the summer, you have a position. You don't have funding, but you have a position. Okay, so I'm going to assume that people are able to understand me. My Boston accent hopefully is not too bad. My spelling, however, is a little bit atrocious. But I assume that this is not too bad and people can make sense of this. Yes? Okay. It's not too bad to actually fix this. There's a small little delay between when it goes from the iPad to the computer, so I will try to anticipate how much time I need to advance things. And so what I want to do today is just, first of all, talk about what am I going to talk about today. I mentioned to some of you, I know how dangerous it is to give a talk around this time of day. Please, please, please be speaking up and answering questions. There's a lot of different ways this talk can go. So many different audiences can go to a talk like this. I was trained as a number theorist, but I was a double major with physics. And because of physics, I never actually took group theory. I never took abstract algebra. I've taught it, but I actually never took it. When I teach group theory, I love to use as motivation cryptography and applications like that. So we'll be doing some applications from number theory and group theory. I was trained as a theoretical mathematician. I married a professor of marketing, and through that, I have a lot of connections with the real world. I do a lot of consulting, and I know that there is a huge difference between what works in theory and what actually works in practice. And so trying to actually apply some of the stuff in real time can be quite problematic for anybody who's done modern day encryption. As time permits, I want to talk a little bit about research questions you can do related to this and other types of problems. And again, if there's ever anything that's not clear, please speak up. Either I or my assistant are happy to assist. So I'm going to start off with a simple test, the Wason 4-card task. Which cards must you turn over to verify the rule that if a card shows a vowel on one face, then it has an even number on the other? So vowel is A, E, I, O, or U. We will allow Y if you really want it. So does anybody know either which cards have to be turned over or which ones don't have to be? Okay, we have to turn over E, good, because if there's not a vowel in the back of E, we're in trouble. We have to turn over E. Anything else that has to be turned over or not turned over? Four has to be turned over because if there's a non-vowel behind 4, we're in trouble. Wait a minute. So the rule is that if a card shows a vowel on one face, then it has an even number on the other. So wait, we don't have to turn over 4. It doesn't matter what's on the other side of 4. 4 does not have to be turned over. E has to be turned over. What about K and 7? We have to turn over K and 7? Just the 7. So a lot of you have implicitly made an assumption. Does anybody know what assumption you're making? You're assuming there's numbers on one side and letters on the other. It does not say that in this problem. It's often meant that way. And a lot of times we know how to interpret things even if it's not written properly. The reason I'm starting with this is, I need to get up to an hour. And need a little bit, no. The reason I'm doing this is it's so easy to implicitly assume things. And a lot of times when you're doing problems in cryptography, you might assume certain things about what you're doing. And I just want to put this in as a warning to be very careful as we go forward. All right, so, even though I was making a joke about how much time I have to fill, we do only have a finite amount of time. So I'm not going to go into all the details. I'm going to assume people have seen enough cryptography that it's enough to just send strings of zeros and ones. I can come up with some kind of dictionary. I can maybe have A is all zeros, B is 4 zeros and a 1, and so on and so on and so on. And so if I can send strings of zeros and ones, I can send messages. And this is extremely important in the 21st century. If you want to buy something online, you are not going to go to the headquarters of whatever place you want, establish a connection. You have to remotely communicate with them and come up with a way to verify that you are who you say you are, and you are authorizing the expenditure of money, and then they will send you what they want. So the two biggest issues, or at least two of the big issues, is you want to transmit messages so that only the desired recipient can read it. And you want to ensure that the correct message is received. So I will only talk about the second one today, ensuring that the correct message is received. Okay. Out of curiosity, how many people have seen RSA encryption? Okay, so not everybody, but a lot of people. So typically you take two very large primes for application purposes, and to fit on the slides, I will use 5-digit primes, but you do something much larger. So you will choose two primes P and Q, keep them secret, and choose a special number D that you will keep secret. And then you will make public the product of the two numbers and a special number E. And this E has the remarkable property that E times D is 1 mod P minus 1 times Q minus 1. So that means when you divide E times D by P minus 1, Q minus 1, it gives you a remainder of 1. It turns out that there are ways to do this, and there are ways to do this quickly. And when you're looking at a number of size 10 to the 200, this is a non-trivial task to do some of these calculations quickly. And the way it works is if you want to send a message, what you do is you raise m to the E for encrypt, and then you look at the remainder when you divide by n, and you send that. And again, if you think of these as 10 to the 200 digit numbers, doing 10 to the 200 operations is way beyond anything we can do. The universe is on the order of 10 to the 80, 10 to the 90 subatomic doohickey whatchamacall thingamajigs. So if everything in the universe was a universe, we're not even close. And you have a supercomputer running since the dawn of the Big Bang. We're not even close to being able to do all of this. But it turns out that there are very fast ways to do this. And then to decrypt, you just raise it to the dth power, divide by n, and you get the message. How many of you have seen something like the Caesar cipher for encryption? So what's really nice about this is it's almost not even needed because so few people could read back in ancient times. Just writing something down was almost enough for security. But what you do is you just advance every letter by 3. And so if you want to transmit A, you want to send A, you send D. And then you just wrap around at the end of the alphabet. So X, well, I can't add 3 beyond X, so X would go to A. And then to decrypt, you just go backwards. If you send one letter wrong with the Caesar cipher, it's not a big deal. The rest of the message is fine. If I receive one digit incorrectly, let's say I received an 8 by mistake, then all of a sudden, when I try to decrypt it, I have almost nothing in common with what the message should be. And if you think about it, if you were to take a message and all the digits are 0 through 9, what fraction of the digits do you think you would get right if you just randomly guessed? A 10. And so if you look at this, I've got 2 right out of 2, 4, 6, 7, 8, 9, 2 out of 9. If I had 1 out of 9, it would have seemed too suspicious, so I jiggled the numbers a little bit until I got 2 out of 9. What this is telling you is it's extremely sensitive. One small bit being off, and the message is completely worthless. So we have to be very sure that we can send and receive the digits we want. Okay, so I'm going to concentrate on error detection and error correction. And a lot of the subject is due to the great Hamming, who, when he was low man on the totem pole, was only allowed to use the computers over the weekend when nobody else needed them. And these are the old punch cards, and you would put it in, and you would come back on Monday, and you would see it ran to line 16, and then it stopped because there was a typo. And then next week you run and you get to maybe line 35. And the story is, he remarked, if the damn machine can detect an error, why can't it correct the error? And so this led to a lot of research in not just identifying errors, but how can you efficiently correct the errors? And the definition of efficiently is going to change as the technology gets better and better and better. I hopefully look younger than I am. I remember working with an old Timex Sinclair 1000, and my dad splurged and got the 16 kilobyte memory expansion for me. Back then, it was really tough to code things now. The amount you have available now is you can afford to be a lot less efficient back then. So the big questions are, how do you detect an error and how do you fix an error? So hopefully people have heard of check digits. Just say, how many people have heard of check digits? Okay. If you haven't heard of it, you've at least experienced it, even if you don't know that you've experienced it. So a lot of times, if it's easy to read again, just do that. So sometimes it's not easy to read again. I actually have a friend who's a mathematician now. He used to work on a nuclear submarine. And so nuclear submarines probably don't want their position to be known, so they would only surface at specific times. So if you transmit a message to them and they don't get it, it may not be easy to send the message again. If we know that a message was sent incorrectly, if we know that a digit was read incorrectly, and we can just send it again very easily, then let's just do that and let's not develop an advanced theory. The hope is that errors are rare. And if errors are rare, just try it again. So does anybody know a situation in life where if something doesn't come out, you just try again? Credit cards, supermarkets, scanners, anything like that. If it doesn't work, just try it again. And if you're at a supermarket and you try it 3 times and the product doesn't scan, what do? Yeah, then they'll just type it in and say, all right, we tried it 3 times, it's not working, we'll move on to something else. All right. So we've all seen experiences with something like that at a supermarket. This is very easy. We're not even trying to correct the error, we're just trying to detect an error. So how does the supermarket detect that an error has been made? So the simplest method is the check digit. And so I will do it 2 different ways. I will do it for those of us who like counting base 10 with the 10 fingers that we have, or those of us who have moved to the computer age and just do zeros and ones. And so the way the check digit works is whatever numbers you have before, I will always use pink as my data and blue as my check digits. You choose for your check digit whatever you need so that the sum is a multiple of 10 up top, or it's a multiple of 2 down below. And so this is not going to detect all errors. If I switch the 1 and the 0 on the bottom, I'm not going to change the sum. But it will detect a lot of errors, and the hope is if errors are rare, then this is enough to let you know that something went wrong. It won't tell you how to fix it, but you'll at least know that something went wrong. Okay, and so in the following, I've changed things a little bit. It's a little bit easier for me to look at the bottom and do the arithmetic there than to do it on the top, and I can clearly tell that something is wrong because it no longer adds to a multiple of 2, it adds to something else. Unfortunately, the error was in the check digit. The message was transmitted correctly. It was the check digit that was, I have no way of knowing that, unfortunately. But it at least identifies that a mistake was made. No talk would be complete without giving references for people who want to learn more. Wikipedia is usually very good with stuff like that. There are more involved methods that allow you to catch not just single-digit errors, but actually flipping adjacent digits. So that if you flip 2 adjacent digits, it will detect an error like that. We want to detect where the error is. So one simple way is the tell me twice. One simple way is the tell me twice. So you just transmit everything twice. And if you don't get 1, 1, and you don't get 0, 0, you know a mistake was made. Is it possible that you wanted to transmit 1, 1, and 2 errors were made and you got 0, 0? Yes, that is possible. The hope is that your system is pretty good and an error is rare, so 2 errors should be exceptionally rare. It's not impossible. Any Seinfeld fans here? All right. The episode The Opposite is one of my favorite. So George Costanza, who is the poster child for loser, is remarking to his friends that every decision he's made in life is wrong. So his friends convince him that he should do the opposite of his instinct. This only works if you are in a binary world, where if you know that everything is wrong, then just do the opposite. And so in terms of the probability of an error, what's the best probability of successfully transmitting a digit for us? If you could choose any probability, what would you choose for transmission success? Perfection, 100%. If you can't choose 100%, what would you choose? What's the next best probability for success? I'm sorry? No. 0. 0 is the next best, because if you know that everything is wrong, then you just flip everything. What's the worst percent of success? 50%, because then you have absolutely no idea what's going on. So we will always assume that we're in a situation where an error is rare, so 2 errors would be exceptionally rare. So we can modify this a little bit to majority rules. And so we're going to use the tell me 3 times method. So now we're going to transmit 111,000. If we get anything other than that, we know a mistake was made. If you get 110, what do you think was meant? If you get 110. 1, right? It's possible that you had 2 errors. Anybody ever see the movie Minority Report with Tom Cruise, based on a good book by, I think, Philip K. Dick, a story by Philip K. Dick? I won't ruin it, but they have a really nice application of this in the movie and the book. So the tell me 3 times method almost surely will detect and correct an error. As long as 2 errors is very rare, if I don't get 111 or 000, almost surely just 1 digit is off and just flip that digit. Okay, so why isn't this great? What? Yeah, you triple the volume of what you have to do. In the 21st century, this isn't actually that big of a deal anymore. In the old days, this was really bad. And if you think about things like the Voyager space probe, where it's sending information with probably 1960s technology, billions of miles, to have only 1/3 of your message being data is quite bad. But it does allow you to detect and correct an error. And so the question is, what can we do to do a little bit better than this? So, only 1/3 is information. We could do the tell me 4 times. And then if we do the tell me 4 times, we're going to be even more confident, but now only 25% of the message is data. Again, in the 21st century, you might be willing to make trade-offs like this. Certain errors are worse than others. Has anybody ever been in an elevator? Okay, yes? You would much rather have the elevator not being used to maximum capacity than to overuse it. So you might want to make your errors go in a certain way. So this is a chance now for really good audience participation. So do we all agree that tell me 4 times is not going in the right direction? So I want to correct errors, and I want to be able to send a lot of information. What will you consider a success? Just so I know what I have to do in the talk today. What will you consider a success?
As opposed to like 1 over n?
Right, so 1 over n, I've got tell me 3 times, that gives me only 1/3 of my message is data. What would you say, if I reach this, I can call myself successful? Better than half, okay, thank you. I was wondering if it's going to be better than half, if you would actually give me a half. But okay, I've got to actually exceed a half, I have to break 50% for you to be happy, okay. And so I did put in greater than a half. I was hoping that somebody would hold me to a high standard. Otherwise, I'd have to talk to the National about the new Phi Beta Kappa chapter here if they have such low standards. All right, so one of the hardest things to do is to look at things new ways. And so let's revisit tell me 3 times, and let's draw it a little bit differently. So rather than drawing the 3 dots in a row, I'm going to draw them in some kind of like L or right angle. Why is this good? Well, I can now look at it as the first blue dot in the row is going to make sure that the row sums to a multiple of 2. And the blue dot in the column is going to make sure that the column sums to 2. So when I do it like this, it suggests maybe what should I do if I have another data point that I want to transmit. And so what I can do is if I want to have another data point, let's put them next to each other, and now I'll have 2 columns and 1 row. And I can go through the combinations. If we only have 1 error, let's assume the error is the upper left data point. If that is wrong, then the blue dot in the top row is wrong, and the blue dot in the first column is wrong. It says there's some mistake in the first column, there's some mistake in the first row. Oh, well, if there's only 1 mistake, there's only 1 element in the first row, first column. Let's assume the blue dot in the second row, second column is wrong. Then I would say, I would detect that there's something wrong in the second column. The first row would be okay, the first column would be okay. Oh, well, then the only issue is there has to be a mistake in the second column, but not in the first row. It's got to be the check digit. So you can go through the rest of the configurations. This allows me to transmit 40% data. Unfortunately, I had to do above 50%, so this is not enough. I could, of course, shampoo mathematics, lather, rinse, repeat, just keep putting more and more columns like this. But that's not going to be great. That's always going to be slightly less than 50%. I can get as close to 50% as I want, but I will be a little bit below 50%. Okay. So we need to find something else. The other thing that's worth noting is there's a natural tendency to, we transmitted one data point, then two data points. Maybe we could try to find a good way to transmit 3 or 4 or 5. Not all numbers may be equally good to choose for how many data points to try to transmit. I might want to try to exploit some geometry, some combinatorics, and depending on how many data points I choose, certain configurations might become available and I might be able to do better. So let me think a little bit about 3 and 4 and see if there are good patterns to do. And so the first is a triangle and a square. Triangle has 3 data points and 3 check digits. The square has 4 data points and 4 check digits. I will just do one. Does anybody want me to check out the triangle or the square? First loud voice wins. Triangle. Blue or red? Blue. All right, so if the blue in the horizontal row is wrong, then it tells me there's something wrong in the horizontal row. Everything else is correct. So the only thing that could be wrong is that check digit. And you can go through and you can see that this will allow me to uniquely determine where the error is. Have I succeeded? Not yet. I am so close though to succeeding. I have come as close to succeeding as possible. I've just hit 50%. Which is better, the triangle or the square? And you can justify both. There is no wrong answer here. Both can be justified as better. Yes, square is better. Now, the hard question is, why is the square better? Well, is it easy for you to make the square bigger? I think we can all figure out how to do the next square, the 9 data points, the 3 by 3, the 16, the 4 by 4. It's really not that hard to figure out how do I expand the square. For the triangle, it's not as clear how to expand the triangle. It's also a little bit more painful to program the triangle. But it's a one-time programming. And actually with all the online programming capabilities now, it's probably not that bad. Just say to the computer, please program this for me. What is the advantage the triangle has over the square? It is. I mean, I'm a Star Trek fan. It kind of looks a little bit like some of the symbols from the Klingon Empire. But there is an advantage the triangle has over the square. There's less intersections, but it's not just the intersections that's less than. It's less. It's not the symmetry. It's less what? What does the triangle have less than the square? I'm sorry? Data points. It has less points total. I'm able to transmit 50% efficiency with 6. With the square, I can only get 50% by using 8. And again, having 2 errors is unlikely, but the more things you transmit, the more likely you are to have 2 errors. So the triangle is actually a little bit better. They both do 50%, but the triangle does it with less. So what should we try to do next? Should we try to do 5, 6, 7, 8, 9? The square is yelling at us to try to do 9. It's not clear what the triangle is telling us to do next. We're going to skip 5 data points. And so I will leave that as an exercise for somebody is, can you find what is the best way to transmit 5 data points? Here is how to extend. So as you said, the square is trivial. And for the triangle, I made my nice equilateral triangle. I have my lines. Almost looks like a Da Vinci symbol or something with a circle going through. And you can check with some work that this is going to do the job we want. And this will get you 60% efficiency. And so I'm at least able to now mark this part of the talk as a success. However, if I wanted to extend the triangle even further, this is going to be painful. The square is not going to be painful. And because the square is so much easier to program, I might actually take a little bit of a hit just for the convenience of programming and how to generalize. A better way to do the triangle is I take everything that was a data point from the previous one, a check digit from the previous one, and I make it a new data point. And then I extend the lines and put in a new point to be the data point. And so I will leave this as something for you to think about as to, could you just keep doing this? Lather, rinse, repeat. Can you make this larger and larger and larger? Doing a little bit of number theory, the number of points on a triangle from this, we're going to have n plus 1 over 2 data points, n plus 1 check digits. So when you do a little bit of algebra, you get that the efficiency is n over n plus 2. So as I get larger and larger and larger, I'm going to get as close to 100% as I want. Here for the square, I have n squared data points. I have 2n check digits from the boundary. So I get also n over n plus 2 when things simplify. But the triangle is a little bit better because I'm getting the same efficiency with fewer points. Okay, so we can get as high as we want. So the question is, can you think of a better geometry to use other than a triangle or a square? Can you give me a better figure? What would be a better figure?
So if we're just transmitting matrices, basically, can we just go to 3 dimensions?
Excellent. So you were not wearing your blinders, right? Because a lot of time people will try to think, is there a better plane shape that we can use? And this goes back to the slide in the beginning with the letters EK47 or whatever that was, that we often put these additional assumptions and constraints that aren't there. And so we could go to 3 dimensions. We could use something like cubes. And so this is a great way to justify buying Rubik's Cubes. And so I have a huge set of cubes. I had to choose either bringing the cubes, CookieMonster, or a good dress to wear for all the formal events. And so I decided the formal events have to go first, and then CookieMonster beat cubes. So if you do a 2 by 2 by 2 Rubik's Cube, what you could do is you could put a data point for each plane. You could almost see the screw coming in like that. And so I would have 6 check bits. And so the cube would give me 8 out of 14 points as data, or 57% for the 2 by 2. The 3 by 3, I'll have 27 data points. I have 9 planes. I get 75%. And so you can keep playing lots of games like this. All the slides are online. If anybody is interested in trying to figure stuff like this out, very interested in terms of what's the best you can do for each number of data points. So we've now got 2, 3, 4, 6, 8, 9. I haven't given you anything for 5. Haven't given you anything for 7. And so what can you do for those numbers? And then you can start playing games and trying to compare how efficient is this relative to triangles and whatnot. So I will have the slides online if anybody wants to do those calculations. You can do things a little bit more generally. It's easy with the cubes. You have n cubed data points. You have 3n planes. So you have n squared over n squared plus 3. This is going to become very, very efficient for large n. You could also use other 3-dimensional figures. And so these are more interesting cubes to solve. But you can also put in your check digits, the centers of the different faces and games like that. And you can see what can you do for something like that. There are also higher dimensions that you can use. And as you start to use the higher dimensions, they won't come in for small data sets, but for larger data sets, you can then start coming in. And then there's the question of, we have 5 platonic solids. I think in a school like this, I can talk about Plato. What do you have in 4 dimensions? Are there analogs of platonic solids? How many are there as you go to higher and higher dimensions? What kind of geometries are available? Just very briefly, there is a great way to do things with 7 bits 4 for data. This is one of the things that's most commonly used. It's the Hamming code mentioned after your Hamming code I mentioned earlier. There's other things you can do, especially if you start worrying about more than one error. And so I will just briefly show you the Hamming code. And it's unfortunately cut off the very bottom of the screen, which says if all wrong is D4. So if you look at the numbering, the data points are labeled 3, 5, 6, and 7. And the check digits are 1, 2, and 4. I've done this almost like a subway line. I've got the blue subway lines, the orange subway lines, and the green subway lines. And so the blue is such that 3 plus 5 plus 7 plus blue is a multiple of 2. Orange is such that 3 plus 6 plus 7 plus orange 2 is a multiple of 2, and so on. Does anybody notice anything about the labeling of these vertices? This is a very strange way to label. Does anybody detect a pattern? Well, the bottom label is 4, 5, 6, 7, but the top is 3, 5, 6, and 7.
Bottom labels are 1, 2, 4.
The bottom labels are 1, 2, 4.
1 plus 2 is 3.
1 plus 2 is 3, yes. But 1 and 2 are not connected. Oh, I see. 5 is 1 and 4, okay. 6 is 2 and 4, yes, okay. And 7 is 1, 2, and 4. So I had not noticed that before. So all the tops are coming from adding 2 at the bottom. So if you do this adding in binary, you don't have to carry. And in fact, 1, 2, and 4 are my first 3 powers in binary. If you wanted to extend this, what do you think would come next? 1, 2, 4, 8. And so I could probably do something up to 15 maybe for the top labels. And so this gives you a sense of how you might try to generalize something like this. You can go and you can play the game with this, and you can show that if there's only one error, this will allow you to detect and correct it. So this is a way to have 7 bits sent. 4 of them are data. So this allowed us to get over 50% using just 7 things. I did get over 50% earlier, but I had to use more than 7 things. So this is a better way of doing it. Just because you don't see something initially does not mean it's not there. As a little bit of a comparison, just for fun, let's say we wanted to transmit 2 to the 12th, which sounds like a lot, but it's only about 4,096 bits of data. We could do a square, we could do a cube, we could do the generalized Hamming code, and you see that the percent of the message that's data goes from like 96.9697% to 99.7. Yes, it's better to do 99.7%, but the gain is not that much. And so sometimes you're willing to take a little bit of a hit. And so I don't want to talk too much about this, but there are some questions for people who are looking maybe for something to try to research. What's the fewest number of check digits you need to successfully transmit n digits and be able to correct up to 1 error, up to 2 errors, and so on and so on and so on. My brother is an engineer, and he is very good at helping me understand what happens in the real world. So let's say we want to transmit this string of zeros and ones, and there's a localized burst of noise, maybe a solar event. If there's a solar event, I might expect the errors to be concentrated. And all of a sudden, this small part of the message might be corrupted, and I could actually have 2 bad digits. There is a really simple way around this. You need to know the entire message, but imagine you know the entire message. Let's break the message up into fourths and transmit everything that's 0 mod 4, everything that's 1 mod 4, everything that's 2 mod 4, everything that's 3 mod 4. Now if I have a burst, it's going to split which ones it's hit. And it's going to be less likely that one burst is now going to have 2 errors in quick succession. So you do need to know the entire message before you start transmitting. But if you know that, there's some huge advantages for something like this. Okay, so there are 2 more things I want to do. I want to talk a little bit about steganography. I was told I have till 1:15, and then we're going to go into cookies, and I want to end with something that will lead into cookies. So I will give $100 to whomever can find the cat in this picture right now. Does anybody see the cat hidden in the picture? Okay. So how do we transmit an image? So imagine we have a grid that's L by W. So we have L times W pixels, and each pixel is going to be a triple. Maybe we'll use the red, green, blue coloring. And what we can do is we will give the values of each of these somewhere between 0 and 2 to the n minus 1. And then what we'll do is we'll transmit a triple of three numbers between 0 and maybe 255. So we have 256 choices for the strength of red, the strength of green, the strength of blue. That gives us a little bit more than you would find in a standard Crayola box. This gives us almost 17 million colors that we can transmit. I am not that good at distinguishing. I really don't need almost 17 million color names. I could do with a lot less and not notice any difference. Because I am in the state of Washington, I will ask if anybody's ever seen the TV show Frasier. There's many beautiful episodes, but there's an episode where he and Niles are talking, and Frasier is very excited. Niles becomes very excited because they've discovered a new shade. I think it was white. That was between the previous shades that they had known about. Oh, you mean this? Yes, now. For most of us, we don't need 16 million. We probably don't even need 1 million. Probably don't even need 10,000. So what you can do is we can conceal a message in another message by just changing the last 2 digits of our number. So we write our numbers in base 2. And so let's take one of our colors, let's say red. It's going to be a number between 0 and 255. So it's going to be 0, 1, 2 to the 7th plus 0, 1, 2 to the 6th, all the way down to R1 times 2 plus R0. If I want to transmit a black and white message, let's let R0 be 0 if we want to transmit black and 1 if we want to transmit white. I can now transmit a black and white message by just changing the last digit of red. If I allow myself to change the last 2 digits, that now gives me 4 colors for red, 4 things for red. I can do similarly 4 things for green, 4 things for blue. That's going to give me 64 possibilities. That can give me a nice, decent image with 64 colors if I just play with the last 2. And it's probably not going to have a huge impact on the color I'm going to see for everything else. And so when I mentioned that there was a cat hiding, here is the picture. The cat was actually the entire picture. And so just, changing the last 2 digits, the cat is everywhere. If you want, you can transmit a message like this. If I want to just take something, take a Word document, write something out, and then it just is 0, 1, black or white for each pixel, I can transmit text. So you could actually hide a message in a message. You could hide a message in a picture. And then there are ways to detect if an image has been modified. And so because this can be used for nefarious reasons, I do not want to talk about how you can detect that an image has been modified while it's being recorded. Okay, so for the bonus to lead into cookies, we are talking about strings of 0s and 1s. And so when I was told that there were going to be cookies after the talk, I had to work in CookieMonster. So I've been the director of the Williams Summer RU program for many years. I've worked with students all over the country. My students really loved CookieMonster this year. He is actually extremely useful in proving theorems. And he's actually gone on tour to a lot of conferences my students have gone to. And so I'm going to show you how to prove theorems using CookieMonster. You may have seen some of these theorems using less exciting names like stars and bars problem, but to me, it's the cookie problem. I want to make sure everybody is on the same page in terms of background. N factorial, has everybody seen factorial? It's the number of ways to choose n objects when order matters. So factorial just means multiply n all the way down to 1. And we define 0 factorial to be 1. There is one way to do nothing. It just makes everything work out nicely. N choose k, n factorial over k factorial, n minus k factorial is the number of ways to choose k objects from n when order doesn't matter. So choosing, say, 3 of you here to get cookies today, that would matter, right? If you are one of the people chosen to get cookies, that's very different than if you're one of the people who's not chosen to get cookies. But it doesn't matter which order I choose you to be one of the 3 people. So which 3 people, that matters. But if I choose you to be first or second or third, doesn't matter. And then the last is Stirling's formula, that n factorial is approximately for large n to the n e to the minus n square root of 2 pi n. There's lots of ways to prove this. If you know the central limit theorem, there's a really nice proof of this using a Poisson distribution converging to a normal distribution. It's a nice one-line proof. It's a good example of using the integral test. If you've done calculus, take the log of both sides. Whenever you see a product, you want to take a logarithm. The log of n factorial becomes the sum of log 1 plus log 2 plus log 3. Oh, well, the sum of the logs is like the integral. So you're integrating log of t dt. The antiderivative of log of t is, of course, t log t minus t. In general, integration is hard, but it's very easy to check and see if I'm right by just differentiating. And so if you differentiate t log t minus t, you do get log t, and that will give you the main term. Okay, so I am also the president of the Fibonacci Association. I was very careful to make sure I chose a name tag for going on tour today that said both Williams College and Fibonacci Association. So has everybody seen the Fibonacci numbers? Okay, and I know there's now a lot of ties between Gonzaga and Italy that are growing over what has already existed. And so the first few are 1, 2, 3, 5. Each one is the sum of the previous two. Some people define the Fibonacci's as 0, 1, 1. I don't want to do 0, 1, 1 for the following reason. There's a beautiful theorem due to Zeckendorf that every positive integer can be written uniquely as a sum of non-consecutive Fibonacci numbers. If I start with 0, 1, 1, well, I could include 0. And if I have two ones, well, which one do I use? I lose uniqueness. So I will define the Fibonacci numbers as 1, 2, 3, 5, and so on. So this is an interesting property of the Fibonacci's. If I give you a number like 51, I could ask, what is its Zeckendorf decomposition? There are a lot of ways to do this. The greedy algorithm is a wonderful algorithm that works beautifully here. What you do is you look at the largest Fibonacci number that's at most 51, and you write 51 as that largest one, 34 plus 17. And I'll light up 34 in red to show that we took it. Now I look to see, okay, what's the largest Fibonacci number less than or equal to 17? At each step, I take out the largest I can. So that's going to be 13. So I'll light up 13. Notice 34 and 13 aren't next to each other. If they were next to each other, well, then their sum is a larger Fibonacci number than 34, and I could have taken that out. And we know I'm too smart to do that because I already broke your 50%. So we don't have to worry about that. So when you do this, you're never going to get too adjacent, and you keep doing this, and eventually we get the decomposition. It's going to be F8 plus F6 plus F3 plus F1. One of the strangest applications of Zeckendorf's theorem is if you are, and this could actually be of use where you are, because Canada is not that far away, right? If you drive to Canada, what do you have to be careful about? Converting. You can use Zeckendorf's theorem to convert. So 83 is 55 plus 21 plus 5 plus 2. What I've done is, if you shift every index up by 1, the golden mean is approximately the conversion factor between miles and kilometers. It's a nice, interesting coincidence. And so if you do that, you could actually convert from miles to kilometers. Now, if you want to convert something like 4, it's not going to do a great job because each Fibonacci number is not exactly the golden mean more than the previous, 1 plus root 5 over 2. But as your numbers get larger and larger and larger, each Fibonacci number is approximately the golden mean more than the previous. So if I gave you something like 4, what you do is write 400, convert 400 to kilometers, and then divide by 100. And that will give you a really good job. So this is one of the strangest applications of Zeckendorf's theorem. And again, when I was a young father, I would do this with my kids and some of their friends as just ways to practice algebra and start doing these things in their head. So why is this related to cookies? Well, I can write my number instead of decimal notation or binary notation, I can write it in Zeckendorf notation as a string of ones and zeros. And now I'm back to strings of ones and zeros, which is what we've been doing, all today. And so this is going to be the Zeckendorf decomposition. I will never have 2 consecutive ones, but I could, of course, have 2 or 3 or 4 consecutive zeros. There's a lot of interesting things you can say and prove. I don't want to go into too much detail here. It turns out that if I look at a number between the nth and n plus first Fibonacci and look at how many summons does it have, it's going to follow a Gaussian distribution. And the reason I chose to look in this interval is I want everything to be comparable. I don't want to look at a number around the 10,000th Fibonacci number and a number around 4. these numbers differ by so many orders of magnitude, they shouldn't be in the same conversation. If I live between the n and n plus first Fibonacci number, they all have Fn as their first sum in their decomposition, so it's fair. It turns out it converges to a Gaussian. You can look at the distribution of gaps between summons. How often do you have a gap of 0? Never. How often do you have a gap of 1? Never. I can't have adjacent Fibonacci. So the smallest gap I could have is 2. And you can ask, how often do I have a gap of 2 or 3 or 4? It turns out it converges to a geometric decay, and the decay constant is 1 over the golden mean. If you have better eyes than I do, although I think I can actually zoom in a little bit, if you look at this, you can see that it's clearly decreasing by approximately the golden mean. No, I can't tell that. So a lot of it is, how do you present data in a good way to make it easy to follow? I just plotted the ratio. And if you look at the ratio between a gap of length k divided by a gap of length k plus 1, you can see it's very close to the golden mean. And then things start to go haywire as you go further out. And there's some reasons for that, but there's some interesting problems that if people are interested in research, we can talk about stuff like that. You can talk about the longest gap. How long do you have to wait? It's very similar to tossing a coin, and how long do you have to wait before you finally get a head or a tail? It's not going to be a fair coin. What I love about this is you get the exponential of negative the exponential of. So if you've ever taught calculus and you've given students differentiate the function e to the x, this is at least a justification as to why you might see something like that. When you look at these probability questions of how long do you have to wait for something to happen, something like this does come into play. All right, so we have less than 10 minutes to get to cookies. We will easily make it. We will not go over. So I call this the cookie problem. How many of you have heard of the stars and bars problem? Okay, it's the stars and bars problem. Okay, but if I say that, I can't justify buying CookieMonster. And so how many ways can you divide C identical cookies among P distinct people? So basically think an engineering professor with grad students, they don't really know their names. They're all interchangeable cogs in the giant lab. No. The people are distinct. These will be like math grad students. The professor knows your name. The cookies, however, will be indistinguishable. I don't care which cookie I get. I may change my mind in about 10 minutes, depending on what I see, but we will assume the cookies are identical, and all that matters is how many ways can you do it. So I maintain a math riddles page, and the very first riddle I posted back when I was in grad school was, if I have 10 cookies and 5 people, how many ways can you do this? And there are people who have solved this by patiently going through all the possibilities. A gets 10, 0, 0, 0, 0. B gets 10, and then they get to 9. And when you start getting to 6, 2, oh my, there's so many different combinations. But some people are patient and they go through without making a mistake. There is a way to do this in your head in one line, and that is to have CookieMonster assist you. So imagine instead of C cookies, we have C plus P minus 1 cookies in a line. And we have the original classic CookieMonster from the dawn of Sesame Street, not the adjusted CookieMonster from today, the original CookieMonster who is always up for eating cookies. So imagine CookieMonster eats P minus 1 cookies. If he eats P minus 1 cookies, that's the same thing as putting in P minus 1 partitions. And that partitions us into P sets. So for example, let's say we have 8 cookies and 5 people. CookieMonster shows up, and CookieMonster now eats P minus 1 or 4 cookies. So I will lighten the cookies that he eats. Everything up to the first eating cookie goes to person 1. So person 1 gets 2 cookies. Between the first and the second eaten cookie goes to person 2. It's not their lucky day, they get 0. And so there's a one-to-one correspondence between the number of ways CookieMonster can eat P minus 1 cookies from C plus P minus 1 cookies and the number of ways to divide C cookies among P people. There's a lot more that you can do with this. This might bother some of you that it's not fair that person 2 gets no cookie. So you could actually put in constraints that everybody has to get at least 1 cookie. Or you might put in some constraint, if the president arrives, the president must be able to get at least 3 cookies. If a tenured professor arrives, they must be able to get at least 2 cookies. You can put in constraints like that. Lower bound constraints are easy. Unfortunately, upper bound constraints are quite hard. To put in a constraint, we know you're hungry, we know you're on the football team, we know you're on the basketball team, you can't have more than 4 cookies. Those are very hard to put in, and there's a lot of problems in additive number theory and combinatorics where it would be great if we could put in constraints like that, but we can't. How is this useful? Well, we can recast this into more acceptable language for math talk. And so what we're really doing is we're solving the equation x1 plus ... xp equals c, where the xi's are non-negative integers. And the number of solutions is c plus p minus 1 choose p minus 1. So every talk is supposed to have at least one reasonable proof. I waited till the very end. I didn't forget about it. Do not try to follow the algebra too closely. Trust me, I've done this many times. I'm pretty sure the algebra is right. Just go for the big overview as to why it works out. So let's let p n sub k denote how many integers in the interval between fn and fn plus 1 have exactly k summons in a Zeckendorf decomposition. I'm actually going to prove more than every number has a Zeckendorf decomposition. I'm going to prove how many numbers have exactly k summons in their decomposition. Well, we know that the first summoned has to be fn. It has to be the largest. And then we have a bunch of other ones. And let's call it I1 through ik minus 1, because we have exactly k summons, and we know the last one has to be n. So we know I1 is less than I2, et cetera, et cetera, et cetera. We know I1 is at least 1, and we know I2 is at least 2 more than I1. We know I3 is at least 2 more than I2, and so on and so on and so on. So whenever you have known information, incorporate it. So let's let D1 be I1 minus 1, and then in general for j greater than 1, dj is ij minus 1 minus 2. I'm subtracting how much I know I must have moved. Well, if I add all the d's, I've basically covered everything. I got to be a little bit careful because of the stuff that I subtracted, so I just put that all in, and that's going to count all the way up to n. So the sum of the d's is going to be n minus 2k plus 1. And so all I have to do to figure out how many numbers have exactly k summons is just count how many ways can I choose non-negative integers to sum to n minus 2k plus 1. Oh, that's the cookie problem. It's just going to be a binomial coefficient, which when you do the algebra is just n minus k choose k minus 1. And so I decided, I guess, not to include the slides. Now that I know that this is n minus k choose k minus 1, you can actually use this to prove that it has Gaussian behavior. And you can say, what happens as n gets very, very large? You can show this converges to Gaussian behavior by using Stirling's formula. It's about 4 or 5 pages of algebra. I think I've got that in the appendix if anybody really wants to see it. It's not pleasant. This is why you have undergraduates. You give it to them, and you know that they will eventually get it. What's interesting is you can generalize Zeckendorf's theorem to other recurrence relations, but you don't have this nice closed form expression anymore, and you need a lot more powerful techniques. You use method of moments, generating functions. It's a lot more painful. But thank you.
Probably have time for 1 or 2 questions and then cookies, or we can go have cookies and ask questions.